Okay, today we're going to start with talking about solids, which is chapter 12. When we think about solids, solids can be as hard as a diamond, or it could be as soft as a wax. Some of them conduct electricity, and really, we know that this really depends on their overall composition. And so when we first talk about the different groups of solids, we can classify them based on what type of bonds they have. So first, we have the metallic solids. Okay, metallic solids are kind of held together by a sea of collectively shared electrons. Now they conduct electricity, whereas an ionic solid, which we talk a lot about in this class, such as sodium chloride or magnesium oxide, these are this combination of cations and anions which are mutually attracted to one another. And these do not conduct electricity. And we know that they're very brittle and fall apart very easily. We also have covalent network solids, which means that we have these different metals joined by an extensive network of covalent bonds. And we see this often with carbon atoms, where they're all connected together through covalent bonds. These include things like diamonds and semiconductors as well. We also have molecular solids, any kind of molecular compound that is a solid, so water as an ice. And we know that water molecules can come together through different intermolecular forces holding them together, such as hydrogen bonding or dipole-dipole interactions. So these are really the four major classifications of solids. Two other types of solids which kind of fall outside of these previous categories are polymers and nanomaterials. Now polymers are long chains of atoms which are connected by covalent bonds. And these different long chains of atoms can then be connected to one another through weak forces. And we're going to see that in not only chemical polymers, but we can also look at some biological polymers as well. Lastly, we have the nanomaterials, which are crystalline compounds. And these are crystals on this very, very small magnitude where they're on the order of 1 to 100 nanometers. And we're going to see that they give them very different properties than larger crystalline materials. And so for a long time, you've really thought that bonding occurs between two atoms that are sharing an electron. But when we look at metals, metals can use an electron sea model, where really the metals are a group of cations in a sea of valence electrons. The electrons are mobile and then shared with all the atoms, or all the ions within this metallic bonding. And so we can see that we have these cations lined up and that the electrons are just kind of shared throughout that, holding them together. Well, this gives them the possibility to conduct electricity, conduct heat. They're very ductile, they're malleable, and this really explains this metallic, or is explained by metallic bonding. So then if we turn to ionic solids, we're most comfortable probably with ionic solids because at this point we've understood that we have cations and we have anions, and those come together to form an ionic bond. And so really in ionic solids, the order is comprised of alternately charged ions. And these ions, as we've talked about with intermolecular forces, are going to have very high melting points and high boiling points. And many of them are very brittle. And in the figure, you can see that how we actually can break these ionic bonds, which is very similar to that in how gemstones are actually carved. And so what happens is as you apply stress in both directions where the arrows are pointing, the cations and anions are then going to start to shift. And the cations are going to line up, and the anions are going to line up to one another. And so now they're going to repel one another, and they break off very easily. Next, we could talk about molecular solids. And when we talk about molecular solids, we have to think about the shape of these atoms, because it's really important because it dictates how efficient the molecules are going to be able to pack together. And so when we talk about molecular solids, we're talking about atoms or molecules that are held together by weaker forces, molecular compounds. And so these intermolecular forces or weaker forces are dispersion, dipole-dipole, or hydrogen bonding. And so like I said, shape is really going to matter for physical properties like boiling point. How well can they stack together? And we can see this when we look at something like benzene versus phenol. So we see that in phenol, we basically have this hydroxyl group, which is different than where we have benzene, where we just had a hydrogen. And you would think that the benzene should be able to pack closer together because it's smaller. But the phenol can actually participate in hydrogen bonding. and allows its interactions to be stronger and thus raises its melting point and boiling point much higher than that of benzene. Next, we have the covalent network solids. Okay? And these are going to be atoms that are covalently bonded with regular repeating patterns of atoms. They usually have high melting points and boiling points. And you can see that in these two examples of diamond and graphite. Now, diamond and graphite are both composed of only carbon atoms. However, you can see that their covalent network structure gives them different properties. We know diamond is one of the hardest known materials, and that's due to its structure. It gives it a very high melting point and boiling point. Whereas graphite is composed of these kind of carbon sheets, and each one of these carbon sheets is then connected to the next carbon sheet through some intermolecular forces, such as dispersion forces. And so the way that these are arranged, it makes graphite very greasy due to the sheets being able to slide on top of one another, where diamond is much more tougher. And so this brings us to our first practice problem. And so in this problem, we say covalent bonding occurs in both molecular solids and covalent network solids. So why do these two kinds of solids differ so greatly with respect to hardness and melting points? So take a second and think about that. Okay, so when we look at these different answers, the answer is actually going to be A. And so the molecules in molecular solids are held together by weak intermolecular interactions, right? Whereas when we talk about covalent network solids, these are all held together by covalent bonds. So then we can turn to polymers, okay? And so we said polymers are molecules of high molecular weight made by joining small molecules. And these are called monomers. So we take monomers and connect them together to make polymers. And so really we have these repeating atoms that line up. And so in the bottom table 12.5, we can see that we have things like polyethylene, these CH2 bonded to CH2, and these are the monomers that are going to repeat to make larger structures of polymers. Polypropylene could repeat, you have polystyrene, or polyvinyl chloride, where these are just repeating units, and these come together to form polymers, where we have either films, maybe different types of kitchenware, packaging, pipe fittings, plumbing, and so these are just due to these repeating monomer units. But we also see this in biomolecules, or in biological polymers. When we talk about proteins, proteins are made up of monomers called amino acids, and these come together to make larger polymer structures such as protein. We have nucleic acids, which these nucleotides can come together to make long DNA strands, which is our overall polymer. We have monosaccharides, which are simple sugars, which come together to make longer polysaccharides, such as starch. And same thing with fatty acids. And so polymers are just these repeating atoms connected by covalent bonds. When we look at these different polymers, okay, the longer the chain, the more the twisting that happens. Okay, and so these molecules you may think of them as a straight line where you have these repeating monomer units, but they actually end up giving these little twists. And so the chains can have a variety of lengths, and therefore they can have very large molecular weights. And we see these materials can be very flexible as well, just like when we see different plastics. When we look at these long chains of polymers, where we can see each gray strand here is an individual polymer, we can actually stiffen these and strengthen the substance by actually connecting them together. And in one process, which is seen in making rubber, we can vulcanize it, or in vulcanization, the chains are going to be cross-linked by these short chains of sulfur atoms, basically cross-linking them together and giving them much more structure and stiffening them. Lastly, we have the nanomaterials, and we said that these particles are very small, somewhere between the 1 to 100 nanometer size. And so people study these all around the world for a variety of different uses. One of the things that we can see is that metals on the nanoscale can have quite different properties than larger samples of metals. So metals in the nanoscale have been divided up so much that they become reactive, or they can melt at even far lower temperatures than their bulk counterpart. And this is really what we see with gold. Because gold, nanoparticles, okay, which are less than maybe like 20 nanometers, are going to melt at a far lower temperature than bulk gold. And when they get even smaller than that, gold is no longer a noble unreactive metal. It actually becomes chemically reactive. And you can also see that when gold on the nanoscale is not actually gold colored anymore. So in this stained glass, this red color comes from gold. It's just on the nano size. And we can also see that we have this solution, okay, which is made up of colloidal gold nanoparticles, and it actually kind of gives off this purplish color. We can even look at carbon on the nanoscale. Okay? And so we can have different carbon nanotubes, which can be made with different metallic or semiconducting properties. And it makes them very strong materials based on the way that they're connected together. We can see this with graphene sheets. We can see this with buckyballs, where buckyballs are clusters of 60 carbon atoms. And it makes this nice buckyball soccer-like ball. Graphene sheets are single layers with the structure of graphite. It makes them much stronger. And so we could ask ourselves, what's the difference between graphene and graphite? So take a minute and think about this answer. Okay, well the answer here is also A, that graphene is just a single sheet of carbon atoms, and graphite contains layered sheets of carbon atoms. Practice problem 12.3 says the picture below shows two different polymers. And I want to know which of these polymers would you expect to be more crystalline? Which one would have a higher melting point? You can take a minute and think about that as well. Okay, well we would expect that linear polymer A, okay, has all these ordered regions, and you get this bonding between these, okay, where they line up, is going to be more crystalline and have a higher melting point than B, because these can separate much easier because they're not really ordered as well. 12.4. What kind of attractive forces exist between particles in the following? So what kind of intermolecular attractions could exist between each of the following? With molecular crystals, covalent network crystals, ionic crystals, and metallic crystals. Take a minute and think about each one of these. You can pause the video if necessary. Okay, so if we look at the first one, which is molecular crystals. Molecular crystals are going to be held together through hydrogen bonding, dipole-dipole interactions, or London dispersion. And we can think about this with water molecules that are going to line up and form a molecular crystal like ice. We have covalent network crystals, which are only connected through covalent chemical bonds. Ionic crystals are only connected through ionic bonding. And metallic crystals are only going to be connected through metallic bonding. The last question is 12.5. Indicate the type of solid for each compound below. You can pause the video here and think about your answers. So when we look at the first one, magnesium oxide, we have metal and a nonmetal connected together, a cation and an anion, which means that we have an ionic solid. Part B, we have, again, a metal and a nonmetal. Mercury sulfide. And here we have a cation and an anion forming this ionic solid. Part C is just a metal by itself. It is going to form a metallic solid. And then lastly, we have HBr, and here we're going to form a molecular compound. We have two non-metals, so this is going to form a molecular solid. That completes Chapter 12.